Okay, so gas collection, simply looking at physically how do we collect a gas to study how many moles we have in the lab. We did this a little bit last time with the air duster lab, and we didn't really worry about this additional little factor that we're going to talk about right now. And it's a small factor, but it can play a role in getting an accurate answer. So first of all, we collect gas by a process called water displacement. Again, with the air duster lab, you've already done this, but it's very simple. You create a gas, maybe through a chemical reaction, maybe just through releasing it from a container, and you just, through tubing, bubble that gas into a container that was previously completely filled with water. That gas is going to push a volume of the water out, and so that gives you the volume of your gas sample. So you can figure out the number of moles if you also have the temperature and pressure. Because if we rearrange PV equals nRT, we know that we get PV equals nRT. We know that rearranged we get N equals PV over RT. Okay? So here's the deal. When we're trying to figure out the moles, in this case, of the oxygen gas that we're collecting, so I'm going to call it moles of O2. I'll put a little subscript O2 down there. We need to make sure that all of these variables are for the oxygen only. All right. Now the temperature, that would be, yes, absolutely. That is, the temperature of the room should also be the temperature of the gas inside the bottle. So that would be okay to use. Whatever the room temperature is, I would plug into my N equals PV over RT equation. The volume, absolutely. Whatever the volume if this were a graduated device, whatever the volume reading is from the side of the bottle would be the volume of my gas. Okay, so volume would be okay to use, and consider the volume of oxygen, just like the temperature would be considered the temperature of the oxygen. The pressure is a little different situation, though. Okay, so the pressure, the problem with counting the room pressure as the pressure of oxygen is that oxygen is not the only gas in the bottle. And I didn't explain that before we did the air duster lab, because we just wanted to sort of get the experience using the ideal gas law to solve it for a number of moles of gas in the container. But it can play a role in getting an accurate number of moles. So let's talk about that. The other gas in the container with the oxygen, and you may have already guessed this, would be evaporated water. So there's always going to be some water evaporating from the surface of this liquid water, and that water vapor actually accounts for some of the total pressure in the sample. Okay, so we just used room pressure and assumed that room pressure was the same as the pressure of the gas in the sample. The room pressure is the same as the total pressure inside the container. But since the gas that we're studying, in the case of this drawing, oxygen, is not the only gas in the sample, we have to account for that water vapor as well. So coming down here, I can say the problem with using PV equals nRT to determine the number of moles of oxygen is that water vapor accounts for some of the total pressure. So what we're going to have to do before we plug in the pressure here and call it the pressure of oxygen, we have to subtract the amount that is due to water vapor. And I'll get to where we find that number here in just a second. But this all comes from Dalton's law of partial pressures. It's very simple. Anytime we have a gas mixture, the pressures are due to each individual gas in that mixture. So if you have, two gases, like oxygen and water vapor, the total pressure is equal to the sum of those two gases. So for example, let's say the pressure in the room is 762 mmHg. That would be the total pressure. The oxygen, so I'm just going to call it P of O2, is unknown. And let's say I'm able to look up the pressure due to water vapor at this particular temperature, and temperature affects how much water will be evaporated, as you might guess. And let's say the water vapor accounts for 30 mmHg in this particular situation. So you could pretty easily figure out what pressure is due to oxygen, right? It would just be 762 minus 30. So when I go to use my ideal gas law to solve for the number of moles of oxygen, instead of using 762 here, I would use 732, right? I would subtract 30, okay? Now, as far as where I got that number 30, I kind of made it up, but you would have to use a table. And you'll notice here on this table, and you'll be given this table, it's actually on the back of the half sheet that you got in class last time. But this gives you the pressure due to evaporated water, or the water vapor pressure, at a bunch of different temperatures. And of course, as temperature rises, you're going to have more evaporation, so more pressure due to evaporated water. So the number that I just gave you, 30 mmHg, if you look over here, that would be the partial pressure, or the pressure due to water vapor, at 29 degrees Celsius. So the water would have to be a little bit warm for you to have that partial pressure due to water vapor. Most of the time, room temperature is going to be around 20 to 25 degrees Celsius, and you're going to have smaller total pressures that you're going to have to subtract, or smaller water vapor pressures that you're going to have to subtract from the total pressure. So let's see how this works. Here's an example problem. So how many moles of oxygen would you have collected by water displacement if it occupies 45 milliliters at 765 mmHg and 25 degrees Celsius? So let's just go ahead and first set up N of O2 equals PV over RT. And I'm just going to set this up kind of all at once. So my volume is 45 milliliters. Make sure you convert that to liters. So that would be divided by 1,000, so 0.045 liters. Okay. Your temperature down here on the bottom is 25 degrees Celsius, so if I add 273, that's going to give me 298 kelvins. The R value, if we're in, it looks like mmHg, is 62.4. Okay. And then the pressure. Okay, so I'm gonna do this in parentheses here. I know the pressure is 765 mmHg, but I'm gonna have to subtract from that because that's the total pressure. That is not the pressure due to oxygen, which is what I'm interested in. Okay, so I'm gonna go up to the table. I'm gonna find 25 degrees Celsius, and I'm going to notice and make sure that you're using the right column, because this table has mmHg and kPa. It does not have atmospheres. So if we were working in atmospheres, we would have to convert our pressure to one of these two. But at 25 degrees Celsius, working in mmHg, we have 23.8 mmHg due to water vapor. So 23.8 is going to be subtracted here. Okay, and that should give us our number of moles of O2. Okay, so I calculated this to be, so N of O2 equals 0.001794, and canceling stuff here, millimeters of mercury cancels with this millimeters of mercury, liters cancels, and kelvins cancel, so of course my unit is going to be moles, which is what I would expect, right? Sig fig wise, it looks like the number 45 all the way back in the original question has 2. So I'm going to actually change this and say N of O2 equals 0.0018 moles. And there we go. We've done a problem.